Today we're going to talk about the two-sample t-test for comparing two means. And again, we'll use our calculator because it's that fancy formula that is difficult to use for degrees of freedom. So we'll rely on technology more. So testing the difference between two means is called the two-sample t-test. And we're going to test the hypothesis about their difference again. Most often we have that hypothesis difference to be 0, but it really can be anything, and you stay consistent with the null and the alternative. We'll find our t statistic, and our standard error will be the same as we talked about with the interval. So when the conditions are met and the null hypothesis is true, this statistic can be closely modeled by a student's t-model with the number of degrees of freedom by that special formula. And then we'll obtain the p-value like we always have and make a conclusion. So back to that pulse rates example where we had the smokers and the non-smokers and talked about their difference in their beats per minute, their resting pulse. So it seems there is a difference. Is there evidence of a difference in the mean pulse rate, though, between smokers and non-smokers? So our conditions are the same as yesterday. We have independent random samples, each is less than 10%, and we are told that the data appear to be approximately normal. Yay, we can proceed to perform a two-sample t-test. Our null and alternative. So the null hypothesis is that there is no difference in mean pulse rates of smokers compared to non-smokers. So we could say mu of smokers equals mu of non-smokers, or we can state it the way that I have given. The alternative hypothesis is that there is a difference in mean pulse rates. So again, just stay consistent with however you write the null, that you have to write the alternative. Two-sample t-test. We still need to know all of our stats. We'll state those, we'll state what the difference is, and we'll state our standard error. These types of numbers are what are important to report. Our t statistic, meaning our sample, how far away is it from what we're expecting? Well, we're kind of expecting that there is no difference, so we're going to compare that to that. So test, two-sample t-test. Underneath stat test, we have stats. Again, our mu1, we're expecting to not be equal to mu2. That's my alternative hypothesis. Again, we're not pooling. So this gives us our t value of how far away our sample difference is from the expected difference of 0. And it also gives our p-value. So the p-value is 1.1289 times 10 to the negative fourth. So be careful that this is approximately 0.0001. Degrees of freedom is about 56. So because the p-value is so small, the observed difference is unlikely to just be by sampling error. We reject the null hypothesis. We have strong evidence of a difference in the mean pulse rates for smokers and non-smokers. Sorry. So in fact, we can be 95% confident that the average pulse rate for smokers is between 3.1 and 8.9 beats per minute higher for non-smokers. Higher than for non-smokers, sorry. This we found yesterday with our interval. So there is statistical significance found with our samples, but it's up to you, us, the doctors, to decide if there's a difference in beats per minute is substantial or not. Then back to the pizza chains. The conditions are the same as the interval. So we have to assume independent random samples and less than 10% of all the ones that are made. And then we'll check for those histograms to make sure they're nearly normal. We can proceed with a two-sample t-test. Here are our null and alternative hypotheses is that there's no difference for the null and that there is a difference for the alternative. This time, again, we did stat edit and put things in list 1, list 2, found our one variable stats on list 1, found our one variable stats on list 2, wrote down what our mean difference is from both of our groups, wrote down our standard error, and then we're going to calculate our t value, meaning how far away our difference is from the expected difference of 0. Two-sample t-test. This time, again, we have data instead of the stats, although you could put the stats in once you found them. But list 1 and list 2, our test is mu1 is not equal to mu2. Again, we're not pooling, and we will calculate that information. That'll give us that p-value and our degrees of freedom. That should actually say times 10 to the negative fifth. So for our two-sample t-test, if you notice at the bottom when I had you calculate, at the other side it says draw. If you want to sketch it, you can. This particular one does not have it colored in for us because it's so far to the right. 4.82 is really far to the right. But remember, this one would be a two-tailed test, so technically it would also be shaded in at the left. So our p-value is super small. So we end up rejecting the null hypothesis. There is strong evidence to suggest that the two pizza brands have different mean saturated fat. This can be followed up with what we talked about yesterday. It does appear that brand D has more fat on average than the brand PJ. So what we did was we found 90% confidence that it's actually between 3 and 6.3 grams higher. Now, the consumer can make that decision if that really bothers them, if it's that big of a difference. That carpal tunnel example, what hypothesis would we test? So we might want to test their mean pinch strength. We kind of expect it to be the same, but then we're thinking, oh, maybe it isn't the same because which one is better? Which one has a higher pinch strength? So we would want to know about their pinch strength after they've had the two surgeries. So the p-value of this test, if we perform given that null and alternative in number 5, was less than 0.05. So if that was the case, that we would, with an alpha level of 0.05 at least, we would reject the null hypothesis. So we would state there is evidence that the mean pinch strength differs after 4 weeks in patients who undergo both surgeries. Results suggest that endoscopic surgery may be stronger on average. And then from there, it would be a good idea to follow up with a confidence interval. Like, how much higher? Is it that much of a difference that we should consider another surgery? We need to talk about all the effects and the side effects, I should say. So the report actually worked on 36 hands, but there were only 26 patients. So in fact, 7 of the endoscopic surgery patients had both hands operated on, as did 3 of the open incision group. Does this alter your thinking about any of the assumptions? Let's explain that. Well, yeah, it's going to matter because if you have 2 hands that are going into there, those are not independent. We would think that they probably are going to have some type of response that's similar, at least, to the similar treatments. So I don't know that this is a good group of independent hands to be tested on. Okay, back into the pool. Here's the thing. Remember when we know the proportion, we know its standard deviation. Then when testing the null hypothesis, the 2 proportions were equal, we could assume their variances were equal, which led us to pool. For means, there is also a pooled test, like the 2 proportions test, but there's no link between a mean and a standard deviation. So the only way we should be doing this is if we know the difference and we know the standard deviations are the same. So this is very rare. So basically, it's never wrong not to pool for the means. We're going to pool for the proportion, 2 sample proportions, but we're never going to right now for us for the means. What can go wrong? Watch out for paired data. That'll come in chapter 24. Look at the plots. Make sure the histograms are roughly symmetric. Be cautious of if you apply inference where there is no randomization. We want to make sure it's representative of the population. Don't interpret a significant difference in proportions or means causally, meaning if I'm looking at the study, one doesn't necessarily cause the other still. That's an important thing to look at. When we use t-models, it's whenever we have to deal with means, okay? We've learned that the reasoning of statistical inference remains the same as we did with proportions. It's only the actual mechanics that change, and we have all those formulas on that reference sheet, so make sure you know where those are. As you guessed it, for the AP, you need to check your conditions. We need to draw those 2 graphs for the small sample sizes, specifically those little histograms. Independent groups are important, random sample. You may not be writing the full formulas for this, but you have to write the name of the procedure, as always. It's really important that you're writing that name of the procedure. It's also important that you're drawing a sketch of the normal curve, or not the normal curve, I'm sorry, the student t-model in this case. So picture, picture, picture. If you write the formula, watch your symbols. Make sure you're actually talking about the sample or the population, whatever you are intending to. X bar or Y bar is the sample mean, whereas mu is the population mean. We're almost there. We're 22, 23, 24 will be on the test together after we finish chapter 24.